In the previous video, we've seen that there are two forms of the power series, this form and this form. So this one here is a simple version of this. So when it comes to the power series, we always want to know for what values of x, the series will converge. So you would use whichever method you want. We've in the past used the ratio test. Well, using the ratio test, it will lead us to this. It will converge when the absolute equals 1. So when you get to this stage here, it means that the radius of convergence here, it has a radius of 1 and is centered at 0. For this one here, it will be centered at A, and then the radius here, the radius of convergence here is 1. 1, but the important here is that when you get to this stage here, it will be centered at A. So this one here is always centered at the origin. This one here is always centered at A. If you don't understand this, don't worry about it. Towards the end, hopefully it will make sense. So let me give you an example of this scenario here. So let's say we've got a function that's defined by this power series. We want to know where we want to know the domain for this function, meaning we want to know for what values of x the series will converge. So when you have a function that's defined by a power series, you're always interested in when it will converge. Well, the values of x for which it will diverge, you're not interested in. So you're always wanting to know for what values of x will make a series converge. Well, let's say you've got a function that's defined by this. So you see, if you use a ratio test, it will allow you to work out for what range it will converge. So for this one here, let's use a ratio test. So with a ratio test, you always want to compute this value here. Get an plus 1 divided by an. So looking at this is your an plus 1. Divided by an is the same as multiplying by the reciprocal of an, which would be this thing here. Now tidy this whole thing up so you can visualize this as being one block multiplying another block. So that's to the power of n, 1 to the power of 1, and then what? Let me think. And then visualize this as one block multiplying the number 3. So now this block here will cancel out with this block, and then this block here will cancel out with this block here, leaving you with this. Okay, so now group all the n's together and all the x's together. So if you look at this, hang on, let me think. Group all the n's together, so that will then give you this, and then group these together, that will then give you this, and then let me think, and then remember, absolute of A times B, that's the same as abs of A times abs of B. So that's the same as this, and then remember, n is from 1 to infinity. So you don't, n is always positive, so you don't really need this. So this thing here will then become this. So now that we're here, remember we've computed this value here. When it comes to the ratio test, we always need to compute this value here. Hang on. an plus 1 over an. Now if this value here is less than 1, then we know it's going to converge. If this value here is greater than 1, we know it's going to diverge. If it equals precisely 1, it's inconclusive. So we want to make this value here, meaning we want to make this to be less than 1 in order for it to converge. So we need this thing here to be less than 1. So for it to be less than 1, so here, as n heads towards infinity, this thing here is just going to go to 1. This thing here is just going to go to 1. So for this thing here to be less than 1, we would need to make this to be less than 1. So we would need to make this to be less than 1. So basically, we are trying to make this to be less than 1 in order for it to converge. So well, this is going to be 1. So concentrate on trying to make this to be less than 1. So concentrate on making this to be less than 1. Now, absolute of A over B, that's the same as abs A over abs B. And then absolute of the positive number 3 will always be positive. So this thing here is really the number 3. Well, times both sides by 3, that will then give you this. That will then give you this. So now once you're here, you can always translate. Once you're here, you can always translate this to this. It means the same thing. So now what it's saying is that the center is at positive 2. So this is your center here, and it will have a radius of 3. So 3 here and 3 here. So your radius will be 3, centered at 2. So what that means is, so remember, this is your center here. This is your center. It has a radius of 3. So anything in this interval here, remember, has to be strictly greater than 3 and strictly less than 3. So anything in this interval, we know is going to converge. Remember, when it comes to the ratio test, if it equals precise, if it's less than 1, we know that it's going to converge. Greater than 1 is going to diverge. We're not interested in this scenario here. We're interested in when it will converge, which will be in this interval here. But then when it equals precisely 1, then it will be inconclusive. So we will need to so when it equals 1, it could still converge or it could still diverge. So we need to investigate what happens when it equals precisely 1, because the ratio test says that it's inconclusive when it's less than 1. So we need to manually check when it equals, well, you see, we need to manually check the negative, we need to manually check negative 1, and we need to manually check positive 5. Because when you put 5 into there, that value which we computed earlier, am plus 1 over am, this value here as n tends to infinity, this value here, when it's 5, this value here equals 1. It's inconclusive right here. And then if you put that, this value here will be 1 also. So we need to manually check this value here, negative 1, and we need to manually check positive 5, which we will do in the next video. But for sure, anything in this interval here, it will center at 2 here. For sure, anything in this interval here, our function will converge, but we need to manually check these 2 points, okay, which we will do in the next video.